Glider 3-4 Aerodynamics of Flight. Today, we delve into the intricate dynamics of turning flight, exploring the critical concept of load factors and their profound implications for glider operation. As pilots, understanding the forces at play during turning flight is essential for ensuring both safety and optimal performance. Now, let's focus on load factors, which represent the ratio of the total air load acting on the glider to its gross weight. When we apply any force to divert a glider from a straight-line flight, stress is induced on its structure, and this force is what we refer to as the load factor. The load factor of 1 signifies equilibrium, where lift equals weight in straight and level flight. However, these factors can be positive or negative, dependent on the glider's flight path. Consider a load factor of 3, indicating that the total load on the glider's structure is 3 times its gross weight. Gravity load factors are often expressed in g. For instance, a load factor of 3 is spoken of as 3 gigaseconds. It is noteworthy that modern gliders are designed to withstand stress of up to 9 gigaseconds, providing a margin of safety in their structural integrity. Now, imagine subjecting a glider to 3 gigaseconds during a pull-up from a dive. The pilot experiences a force pushing them into the seat equivalent to 3 times their weight. This effect has become increasingly significant with the heightened operating speeds of modern gliders, necessitating careful consideration in the structural design of these aircraft. Moving forward, when attempting to enhance turn performance by increasing the angle of bank while maintaining airspeed, it's crucial to be mindful of glider limitations due to the effects of increasing the load factor. Knowledge of load factors becomes indispensable for pilots, as it can prevent the imposition of dangerous overloads on the glider's structures. The importance of load factors extends to 2 distinct reasons for pilots: the potential for imposing dangerous overloads and the fact that increased load factors elevate stalling speeds, making stalls possible at seemingly safe flight speeds due to heightened wing loading. In a constant speed turn, the angle of attack, AOA, must increase to generate the additional lift required to overcome centrifugal force and inertia resisting the turn. However, as the bank angle increases, there is a corresponding increase in AOA, leading to a stall when the critical AOA is exceeded in a turn. Let's delve into the rate of turn, denoting the time it takes for a glider to turn a specific number of degrees. All gliders, when flown at the same airspeed and angle of bank, turn at the same rate. Changes in airspeed and angle of bank directly affect the rate of turn, with an increase in airspeed or angle of bank resulting in a higher or lower rate of turn, respectively. Next, the radius of turn refers to the horizontal distance an aircraft covers to complete a turn. This radius varies with the square of the airspeed, meaning doubling the airspeed results in a 4-fold increase in the turn's radius. In thermal soaring, understanding the radius of turn is crucial for maximizing altitude gain, allowing gliders to fly closer to the thermal's rising core. Turn coordination is vital for maintaining optimal glider performance during turns. Proper coordination of rudder and aileron inputs is necessary to avoid slips or skids. Aileron input, with the raised aileron on the inside of the turn and lowered on the outside, affects lift and drag, causing adverse yaw. Longer wings in gliders intensify adverse yaw, requiring coordinated use of rudder and aileron to correct for optimal turn coordination. Now, we delve into the nuances of slips, a flight maneuver that involves a descent with one wing lowered in the glider's longitudinal axis at an angle to the flight path. Primarily, slips serve 2 purposes: to steepen the approach path without increasing airspeed, useful for landing descents, and to counteract drift caused by crosswinds. In the past, slips were standard for controlling landings in short or obstructed fields. However, with advancements such as wing flaps and spoilers on modern gliders, slips are now predominantly employed in crosswind and short field landings. Even though alternative procedures exist, pilots must still possess the skill to perform forward slips, especially when correcting landing approach errors. The impact of a glider's wing planform on slips is noteworthy. In gliders with a rectangular wing planform, slips have minimal effect on lift production, except for obscuring the wing area with fuselage vortices. Tapered or swept wings, however, introduce variations in lift production due to the relative wind's influence on each wing. Consider a glider with tapered wings in a slip. If the left wing is lowered, the relative wind aligns more with its chord line, increasing airflow and lift compared to the higher right wing with angled relative wind. Extreme differences in airflow, as seen in the flight envelope extremes, may lead to the higher wing stalling and possibly an inverted spin. Pilots should consult the Glider Flight Manual, GFM, to understand their glider's slip-related limitations. It's crucial to acknowledge that the use of slips has limitations. Some pilots may attempt to lose altitude abruptly through violent slipping, leading to unpredictable outcomes, particularly in short-field landings. Excessive speed resulting from such erratic practices may cause overshooting the landing area. During the last phase of a final approach, if a slip is employed, aligning the glider's longitudinal axis with the runway just before touchdown is essential. Failure to do so can impose severe sideloads on the landing gear and induce violent ground looping tendencies. Discontinuing a slip requires leveling the wings, releasing rudder pressure, and adjusting the pitch attitude to normal glide levels. Now, let's explore two specific types of slips, the forward slip and the side slip. A forward slip involves aligning the glider's direction of motion with its pre-slip direction, primarily used to dissipate altitude without increasing speed, especially in gliders lacking flaps or with inoperative spoilers. The side slip, on the other hand, maintains the glider's longitudinal axis parallel to the original flight path while changing the flight path's direction based on the bank's steepness. In conclusion, slips are intricate maneuvers with specific applications in glider operations, and understanding their principles and limitations is essential for pilots aiming for precision and safety in various flight scenarios. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.